Welcome to the second video in Frontiers in Physics titled The Principle of Least Action. The principle of least action is one of the most important ideas in physics. Using this tool, we can solve all problems in classical physics essentially. And in these lectures, we are not only going to use it to solve classical physical problems, but it will be a key element to describe what's actually the ultimate goal of this module, that we build up quantum field theories. In this lecture, we will apply what we have learned in the previous lecture. We will apply the line element and that its invariant property. And we will also apply what we just learned about the principle of least action. And using these two things, we will build up the Lagrangian and the action of the simplest relativistic system. From that, we will derive the concept of the form momentum. And using that, we will get back to something that is familiar to everybody. That's Einstein's E equals mc squared formula. And also we will discuss how that is just a special case of something bigger. The other direction we will take is that we will go into the direction of classical field theories. Classical fields are used to describe things like fluids in physics or the formations of solids, for example. However, this principle of least action is something that could be applied to these field theories as well, classical field theory so far. The only thing which we need to modify is that we move from the Lagrange function to the Lagrangian density. So let's get started with introducing the principle of least action. The principle of least action is one of the most important principles in physics. It governs the world from the fundamental up to the whole universe, cosmology. So the first thing to discuss here is that is called the Lagrangian mechanics. So Lagrangian mechanics. So Lagrange was a French person, mathematician and physicist, and so Lagrangian is a function which we define. First of all, we denote it with L, and we define as the kinetic energy minus the potential energy. So T is the kinetic energy, and the V is the potential energy. You could also think about that the total, so if we add these things, T plus V is the total energy of the system. We will see later why this was defined like this, but because of now, this is the Lagrangian function. And so next thing to define is the action. So the action is going to be denoted with S. So the action is the integral of this Lagrangian by time. So we integrate from 0 to up to a certain time that I can call t0. So L was a function, and now this S is, mathematically speaking, a functional. So S is a functional, and L is a function. So functional is when you are integrating a function. Okay, so I mentioned that the T was the kinetic energy and V was the potential energy. So let's just input these things into this definition of the L. So let's just say that here in this L is going to be the same as 1 over 2 the mass of the object and then the velocity of the object. But I'm going to call the coordinates is q instead of using x or r or something like that. So q is the general coordinate. So then when we calculate the kinetic energy, that's 1/2 m times v squared. So how do we calculate the v? Well, that's essentially the derivative of the q. So q is the general velocity. So here I am putting q dot, and as we just mentioned, we need to have v squared. So this is going to be q dot squared here. And then from that, we subtract the potential, which just depends on this q, and it doesn't depend on q dot. So I just inserted what L was. So for the action, we still need to make our integral from 0 to t0 to get s. So the consequence of this is that this s functional depends on q through the v and q dot through the t, the kinetic energy. And essentially, what we want is we want this action to be the least, right? That was the naming. So we want to minimize this action. So mathematically speaking, this minimalization is denoted with this delta. We want the delta s to be 0. So then we have a function, and then to get the minimum or maximum function, we make the derivative of that, we set it to 0, and then where that happens, that function has a minimum or maximum. So the mathematics that's doing the same thing for a functional is called calculus of variation. So calculus of variation. And actually it goes back to a problem which is called the Brachistochrone problem, which states or was asking about that we should find the shape of a curve down which a bead sliding from rest and accelerated by gravity will slip without friction from one point to another. So I can write it down that historically starts with having a point here and having a point here, having gravity acting on an object, and asking what curve is doing that the fastest. So you could think, okay, is it just a linear function, or is it something like this? Is it like a sine function, or what? What curve is describing the least action? So the change in time, I should change it to color. The change in time is the question, and then essentially what is the minimum delta t. So earlier we discussed that we are looking for this thing here, and to solve this we can use two methods. One of them is called the discretization method. So discretization method, and the other is based on partial integration. So for now, we will use the discretization method to figure this out. So we will make the Lagrangian function to be a discrete function. So from the s equals the integral of the Lagrangian by t, we will move to saying that this integral should become a sum, and then we have like these little parts of the function, and then the time is changed from dt infinitesimal to delta t, some longer time period. And we are summing for I. So we need to make the coordinates discrete as well. So when we speak about the qt general coordinate, we will use instead qn point plus the next point qm plus 1 divided by 2. So this method gives us back the continuous function if we have a ton of points. So just some visualization. I have one point here. I have one other point here. So with this method, what we do is that we put a point in between the two. And then the next point, we will put point in between these 2 points. And then the next point, we put point in between these points. And then we go on like this. I could do another with this light blue, for example. Here, point, point, point here, here, here. It's half of each period. And so as we go on, if I continue this to infinitely many points, I get back the continuous function. And then the other thing we need to discretize is the derivative of this q. So there, essentially, we can think about what is the derivative of a function. So if you don't remember that, you should go back to one of the videos which is describing derivatives and functions. But essentially, the derivative of a function was that it will take a limit of delta t to for a function in a point, qm plus 1 minus qn, so the point before that, divided with this delta t. That was the definition of our of a derivative. So now that we are discretizing, we will just say that, oh, I don't care about this limit part, and just this part will be my description of the derivative of the function. Let's put this all back to the function of the for the derivative for the action. The action s is the same as the sum for I of Li delta t, and then how we discussed that this Li depends on, well, earlier we discussed that it depends on q and q dot, and now we express those q and q dot with these qn points. So it's qm plus qn plus 1 divided with 2, as was this qt, and we have qn plus 1 minus qn divided with delta t. And I should not forget this delta t in the end. So it's a sum of I elements, and we can just think about two elements which are next to each other. So we can just say that this is the same as, having some I equal 1, so q1 plus q2 plus so on. So we will reach a point where we have Li minus 1 plus Li plus I plus 1 plus Li plus 2, and so on. So I am again just doing the dot here. So we just took two elements which are next to each other, and so let's just input I minus 1 into the point where we were discussing n earlier, right? So I'm just looking at one point, and that point is located at the I minus 1 location. So that's just going to be, again, it's a sum for I, and then we have the Li minus 1, and so I am inputting this to Qn, but then if n is I minus 1, then this is going to be Qi minus 1 plus Qm plus 1 from here. But if n was n minus 1, then n minus 1 plus 1 is just going to give us Qi here. we divide that with 2. And then we have qn plus 1, which leads n minus I minus 1 plus 1, again just leads to qi. And from that we subtract qi minus 1, and this all is divided with delta t. And then the next element is where L was in the I position. So that's just easy. Everywhere where we had L, we just replace that with I. So that's Qi plus Qi plus 1 over 2 plus Qi plus 1 minus Qi divided with the delta t. And I close this bracket, and I can close the big bracket as well. So now what we could do is that we could, since we're looking for an extremum of this S, we could derive by the Qi point. So I still have my summation for I. I have the bigger bracket, and then I have 2 points to derive in. So the Li minus 1 is derived so it has two coordinates. This one was qt. You should remember this was q dot t. So I derive this by qi, and I don't really know what is the exact form of L, so I am just writing this in as it is. But then I can apply the chain rule and see that okay, so what's the coefficient, or what's the derivative of what's inside of this function? What is the derivative of this variable? And so I see that there is a qi minus 1, which is derivative by qi is 0, but there is a plus 1/2 qi here, which I derive by qi. I will get a 1/2 factor out of it. And then I do the same thing with the next part of this function. So I actually forgot an I minus 1 here. So I take the derivative of Li minus 1 by the other parameter, by this thing. But so you remember that this was the definition of q dot I. So when we do the derivative by q dot I, again, we see that there is a part which goes with I minus 1, so its derivative by qi is going to be 0. But there is a qi term here in front of which there is delta 1 over delta t. So here I have a 1 over delta t coming from inside of this using the chain rule derivation. So this was the Li minus 1. And then I will have very similar things for the Li. So again, I have a 1/2 in front of the Qi. So I have a 1/2 derivative of Li by Qi. And I add to this the derivative of Li by the Qi dot. But then when we look into the chain rule, then we see that the coefficient here is minus 1 over delta t instead of delta t. So I have to fix this, and I have to remove this plus sign and make it a minus sign. So this was now my derivative, my derivation by qi of this function. So we see terms which are very similar, and so we could rearrange this a bit and say that, well, this is still a summation from I, and I have this bigger bracket, but then I have a 1/2 derivative of Li minus 1 divided with not divided by, derived by Qi, which is this term. And then I have this term here, that's 1/2 derivative of Li by Qi. Then I have these terms with the 1 over delta t of Li minus 1 derived by Qi dot minus 1 over delta t of the derivative of Li by Qi dot. Okay, so what do we see here actually? This is if we change back and say that delta t goes to 0, and this is actually a derivative by time, by t, of this L function. So actually a minus derivative, because we have L minus 1 here, and in the definition of the derivative, we need to have the second thing first. So if I exchange these two terms, so I add an extra minus sign, then I get the derivative of this L term by time. So this leads to a derivative by time of this derivative of L function by Q dot. And this will lead to 1/2 plus 1/2 will lead to a derivative of L by Q. And so what actually I should say that I did go back to the continuum limit. Go back to continuum limit. Okay, so what this whole thing was equaling to the derivative of the S action. But earlier we said up here with blue that we want this delta S to be 0. So if this left hand side is here 0, then everything down here is going to be 0. So from this what we get is oh yeah, I was speaking that this goes to negative derivative, but I just didn't. I was speaking about it, but never wrote down that that's a minus sign here. So I have something minus something, and this equals to 0. So we can rearrange that and say that the derivative of L by Q general coordinate is the same as the derivative of the L by Q dot general velocity derived by time. If these two things are the same, that means that we have the least action. So this is called the Euler-Lagrange equation. Euler-Lagrange equation. And if it is true, then the action is minimal, or the least. So if this is true, that means that when we input something to this, then by going through this machinery of the Euler-Lagrange equations, we will get the equations of motion of any problem in physics. So this is the solution to all problems in classical mechanics, and also everything with the quantum field related to this. So these outputs the equation of motion, and so by that we can say that this is the solution any problem. So next thing I want to define is the general momentum or generalized momentum. So that is just going to be, you denoted with P2, that is just the derivative of this Lagrangian by the Q dot. So we could rewrite these equations and with the P in it. However, we will define something else first. This is the okay. So this was the generalized momentum. And then next thing to define is the Hamiltonian. Hamiltonian will be a function h of this generalized momentum and the generalized coordinate. So the Lagrangian was the function of q and q dot. Now the Hamiltonian is a function of p and q. There is no q dot in it. So we define the Hamiltonian by doing the sum of p, q, I, so the generalized momentum times the generalized velocity in each direction minus the L. This, by the way, is also called the Legendre transformation. That's the mathematical direction to go. This is the Lagrange transformation of L. Okay, so we could just think a bit what this really means. So in classical physics, P was defined to be m times V, and so Q dot is V, and the L was kinetic energy minus the potential energy. I was denoting the kinetic energy with uppercase T, where we calculate the kinetic energy by doing 1/2 times mv squared. So the Lagrangian is 1/2 times mv squared minus v. So if we put all these together, I have p, which was mv, multiplied with q dot, which was v, so that's m squared, minus 1/2 mv squared minus of the minus of the v, so that's a plus v. And if I subtract 1 mv, if I subtract a half mv squared from mv squared, I will get a half mv squared plus v. But again, the half mv squared was just the kinetic energy T. So this is physically gives us the total energy of the system. And so we could actually derive equations of motion from the Hamiltonian mechanics too. So Hamiltonian mechanics is using two equations. It's using that the derivative of the p vector, so I'm not writing pi anymore, is by time is the same as the negative derivative of the Hamiltonian by the q vector. And we also say that the derivative of the q general coordinate by time is the same as plus the derivative of the Hamiltonian by the b. They look very symmetrical, right? And it's two equations, and they also lead to the same equations of motion. with the same equations of motion as the Euler-Lagrange equation. Now let's start to search for an action that describes the mechanics in a relativistic way. So 2.2 is going to be relativistic mechanics. And we have a subsection just to start with, that what we were building up. That 2.2.1 is the action. We are looking for the relativistic action, and from that we get the equations of motion going through what we just learned. Let's just look the simplest invariant action, the simplest, and then invariant. That's important. So what's the simplest invariant parameter or number that or quantity that we learned in like last video? Well, that was the arc length. So the simplest thing we can do is just to say that the action is the integral of the arc length, and we allow it that we can put some alpha contribution coefficient there, and since the ds has a maximum, we need a minus sign, and we say that alpha is positive. We have alpha of the integral, and then put the definition of 1 minus v squared over c squared under a square root times c, and we can then move to the integration variable to be dt. So that was the definition of the ds, and we also moved on now with this that the integration is done by time. So integration variables are some t1 time to some t2 time. And actually, you should remember that the s was defined to be the integral of the Lagrangian by time. So with this, we actually have that dt here, and we have an integral here, right? So that means that the rest is going to be the Lagrangian function. So very quickly, because that the Lagrangian is the same as minus alpha times the c. I just move this out here, and we have this formula for under the square root 1 minus v squared over c squared is apparently the Lagrangian of the simplest mechanical system, which is relativistic. To figure out this alpha constant, we can go again to a special case. So special case is if we do to classical mechanics. So how do we go to classical mechanics? Classical mechanics is the same as relativistic mechanics, just the speeds are much less than the speed of light. So to do that, then we can do the Taylor expansion of this square root equation. So Taylor expansion of the square root is what can help us. And then, since the v is going to be much slower, much slower than the speed of light, we can easily just neglect certain terms and get back what's the That's the classical way. Okay. So actually, there is a video for Taylor expansion in my mathematical backgrounds for physics videos. So you should check that out and what you get if you don't know what Taylor expansion is in detail. And so essentially, the outcome of this is that we have here the minus alpha c, and then coming here Taylor expansion is that we have a 1, we have a minus v squared over 2c squared, and then to this we have terms which go with v to the 4 over c to the 4. But just think about it that v was a very small number. So fourth power of a small number is going to be a tiny number. And if we divide that with the fourth power of the speed of light, which is a huge number, then this ratio gives us negligible contributions. So I'm going to just use this order big O notion and say that we don't care about anything that goes with those terms. So if I do the multiplications, then I get that this is minus alpha c plus alpha over 2c of v squared, and the terms which we don't care about, v4 over c4. So then this means that we have some kind of constant plus alpha over 2c v squared. Okay, so then we have a classical system in which there is no interaction. So there is uppercase v0 means non-interacting system. Then we have L, if this is true, then L is just T, and that in classical mechanics that was 1/2 mv squared. So now we see that, oh well, I have a v squared here, I have a v squared here, I have a 1/2 here. So from this, we can, from putting these two things together, we find that alpha is mc. And that was it, right? We get from this, from all this, we get that the simplest action is minus mc integral of the S line element, and the Lagrangian of the system is minus mc squared, and we have this square root of 1 minus b squared over c squared. Okay, the next step, what we can do is that we can think about what the momentum is. So this is 2.2.2 is the 3 momentum. So earlier we were discussing that pi we get by deriving the Lagrangian by the qi dot, the general velocity. So I can rewrite this, that this is the L of the I. Okay, so when I do the derivative of a square root, that's going to be 1 over the square root. So I have 1 over the square root of 1 minus b squared over c squared. And then we do the derivative of what's inside of this function. So derivative of 1 is 0. Derivative of b squared over c squared by v is going to give us 1 over c squared. And so that is actually destroying the c from here. And I also have a minus here. So in the end, this will become a plus. And I have mv here. Oh, there was one more thing which I didn't write out, is that we have now the derivative of v squared. That's going to be 2v but then the derivative of the square root was also giving us a 1 over 2, so those two are also cancelled, and that's how we get this. And if you remember that this 1 over the square root of stuff was defined to be this gamma parameter, this is MPI gamma. This gamma was the Lorentz factor which we defined earlier. So if I go back to the vector notion, this P vector is the same as M times gamma times the V vector. And then if in the special case when V is much less than C, then we just get back that P is the same as MV, right? Because it's just it's going to become 1 here, and the square root of 1 is 1, so that's just MV. Next thing which is interesting to look at is Newton's first law. So 2.2.3 is Newton's first law. So in classical mechanics, we learned that F vector is the same as M A vector. So sometimes I use this underscore for a vector notation, sometimes I use this arrow. So I was using the arrow here because it looks a bit uglier with the P, but it's kind of fine with here. I usually use the underscore notation for vectors. So the question is if this is still true in a relativistic mechanics or not, right? Because the MA was true classically, and now we are asking, is it still true? Still. We will have two different cases to look at. First, we say that well, this velocity vector should be constant. I mean the absolute value, so the magnitude of this vector is constant. And the other case is when the direction of this will be constant. So fi, the ith component of a vector, is the same as the derivative of the ith component of the momentum derived by time. And that leads to saying that since the v constant was v absolute value was constant, we can take that out of the derivatives and just say that from here, this essentially just means that this is m mass times the gamma Lorentz factor times the derivative of the I by t. And so the question is that is this the same as m times a? If we look at that this v vector's direction is constant, so v's direction is const. So in this case, fi equals the derivative of pi by time. So in this case, I cannot actually say that the gamma factor can be taken out of the derivative since its value can change, right? So it is a time-dependent quantity, and so its time derivative will be non-zero. It's not a constant anymore. So it's going to be the same as m times the derivative of the gamma b. If we do the derivative, what we get is that this is the same as m divided with 1 minus b squared over c squared, and then we get a 3 half power here derived with derived with the velocity by time. So is this the same as ma? So we have a term here, which is the derivative of the velocity, and we have the same derivative of the velocity here. However, if you look at the coefficient in front of it, this is m gamma here. This is not m gamma here. This is m gamma um, times square root of that. That means that f equals ma, f equals ma is not true anymore. But saying that f is the same as the derivative of p is still true. So that's it for Newton's equations. Now we kill them with, if we go to high speeds, it's not going to be true anymore. Okay, so we should look at energy as a next quantity. So this is going to be 2.4 energy. And we earlier discussed that the total energy of the system can be expressed by the Hamiltonian. So the energy is the same as the Hamiltonian, which was the sum for I of P I Q I dot minus the Lagrangian function. So I can again change a bit of the notion and just say that, oh, this is Pi Qi dot sum together is the same as the dot product of the P and the V vectors. From that I subtract the Lagrangian. Okay, so P was the same as M times gamma times V. That was our P vector down here now. I'm sorry, this is confusing. I should fix it and just follow up them. And but I am using the down here because if I put it up here, then they are just too crowded up there. And so when we multiply m gamma v with v, we get m gamma v squared. And then the Lagrangian was given to be mc squared multiplied with this it was this mc squared multiplied with this square root. And so if you think about it, that this is the inverse of the gamma Lorentz factor. So I'm just going to divide this with gamma. And please also note that it is a minus sign, but up here the Lagrangian was also minus, so those two minuses will create a plus here. Okay, so if we go ahead and just take out one gamma factor, since that seems to be here, then what we find is that this is mv vector squared plus mc squared over gamma squared. Doesn't look like that it's helping us, but in a second we will see that if I introduce what the definition of the gamma was, that was 1 over the square root of v squared over c squared. So I get that this is mv squared vector plus mc squared times the square of the 1 over square root of things. So the square of 1 over square root is just going to give us, and it was also divided. So when we divide 1 over something that's reciprocal, it means that this goes up here, and we relate to 1 over 1 minus v squared over c squared. And so we should not forget that all of this was divided with the square root of 1 minus v squared over c squared. Okay, so let's just extend that parenthesis here. We have an mc squared term, and then we have an mv squared term, and then we have a minus mc squared times v squared over c squared. So those c squareds are cancelling each other. And then there is one more thing, that we have now mv squared minus plus mv squared plus these terms are also cancelling each other. And what we left it in the numerator is just the mc squared, and then we have the square root of 1 minus v squared c squared here. So going back with the other notion, this is mc squared with the gamma factor. This is something which is probably looking familiar, that if in the special case, this is only a special case, I should really stress this, that if the velocity is 0, then from that we get that the gamma is 1. So from that case, in a special case again, it's special case, we get that E equals mc squared. And that should look familiar from anywhere, but really, this is a very rare special case when things are not moving, also not that interesting, but this really got famous. Einstein, this is all Einstein's work. Now that we discussed the 3 momentum, let's discuss the 4 momentum. 2.2.5 is the 4 momentum. So I hope you remember that there the notion was that it's a p mu, right? If we're discussing x mu as the 4 coordinates, so now this is going to be noted with p. So to get the 4 momentum, we will look at the variation of the action. So we have the delta s, which was the minus mc, and then we have the integral of ds. So we want to vary this. Mc is a constant, so there is nothing to vary on that. So this is the only part which we can vary. And we're going from point A to point B. And you should also remember that the ds was, or the ds squared was dx mu down with dx mu up. So from this, the ds itself is just the square root of dx mu times dx mu up. So if we take the derivative of this, we get the delta of the ds. This is square root function. So the derivative of a square root function is the 1/2 of 1 over the square root of these things. And then I multiply this with the chain rule what's inside here. But then both of these are functions. So it's going to be the x times y derivative rule. So that is the delta of the x mu times the dx mu up plus the dx mu multiplied with the that. Oh, sorry, I got some mistake. That's exactly the same. So now what I do is that I vary only the second. So this is the dx mu, and now the variation of the dx mu up here. The index, if it's a covariant or contravariant variable, that doesn't really change the physics. So these things are essentially the same. And what is down here dx mu is defined to be ds. So I have a thing, what a thing plus a thing is two things, divided by 2, which is one thing. So this leads to either saying that it is the dx mu times the delta of the dx mu up, and this thing down there, the denominator, the square root of that is the definition of ds. So the variation of ds is dx mu times the variation of the dx mu divided with the s itself. So we can put this back and say that then the delta s is the same as the minus mc integral from a to b of this ratio of dx mu times the delta x mu up here divided with the ds. Okay, you should note that this here, the dx mu divided with the ds is the derivative of x, and that was our definition for the 4 velocity. This is u mu. This is mc integral from a to b of u mu, and then we have the delta x mu in the top part. So the next thing that we want to really evaluate this integral. So I have, we will do the partial integration method. So that means that I have minus mc, and then we will take out the u mu and take the integration for the delta x mu. So that's going to give us a u mu here, and then the integral of a derivative of something is the something at the boundaries. So integral of the derivative of x mu, delta x mu, is delta. So this is the delta x evaluated at a and b. And then we have the other terms, the minus of minus, which will give us to a plus, and we do the integral by doing the derivative of the other term. This is delta x mu, and then we take the derivative of the u mu by the s, and I do the s again. So when I multiply these two, I just get 1. I didn't really do anything here, but it does make it nicer. However, when we do this, the endpoints are fixed. Let's fix the endpoint. So if we fix the endpoints, then what's the change in them? What's the change in the XA if we fix them? Fix them means that we don't change them, so the change is going to be 0. And that's the same thing as fixing the other end, which was denoted with the x b. That's also 0. So then this term is zeroed out. By doing this. And then the principle of least action says that this delta s is 0. That means that this whole thing is going to be 0 again if we apply the principle of least action. And that's what we want to do, to find the form momentum. So all this means that delta S is the same as, keep this part only, we only have left it that part, which is then the integral of delta x mu du mu divided with ds and multiplied with ds. That's the same as 0. I didn't write out the MC part because I can just divide with that. That doesn't really modify anything when things are 0. So this has to be true for all changes in the path. So if this can be anything, then the only way that we get this to be 0 is to have the du mu ds to be 0. If we fix the original point, if we say that the delta xa is 0, but the endpoint can be anything, but the delta of xb is the delta x mu, then what we get is that the delta s is the same as minus mc. I could just keep it. I mean, I originally could keep it too, so there is nothing really wrong with writing that there is this MC here. It just doesn't matter at that point, but it will matter this time. So we will have MC u mu, and then we have the delta x mu. And so the reason why we did this is that the definition of the form momentum was that depth of p mu is that it is the derivative of the action by x. So putting these two together, we get that the form momentum of the system is the same as, oh, and there is also minus sign here, as minus minus, so that's a plus, of mc u, and then I have an index. That's how we get the form momentum. We multiply the 4 velocity with m, the mass, and the c. So that's very similar, you know, similar to saying that the p vector is the same as m times v vector in if class. So this is very important for the following. So we just said that the p mu is the same as mcu mu. And so we remember that the u mu was dimensionless, and we proved that by saying that u mu with u mu up was 1. If I put these things together and I say that I want to take the square of p, that means p mu down with p mu up, that's the same as mc times u mu times u mu. But then the u mu times u mu was 1, so this leads us to m squared c squared. And we can also think about what are the components of this four vector. Component of P mu. So the P mu has the first term to be the energy over C, and the rest are the P vector. I really want to write out all the four components. This is E over C, this is Px, Py, and this is Pz. So we can think kind of about saying that like energy is the same thing as momentum, just in the time coordinate, if that makes any sense. But then I can make P squared out of this too. I can say that P mu, well, so P squared, the same as P mu times P mu up. And so how do we do a dot product? Well, that is the first component with the multiplied with the first component, and then plus we add the second component with the second component, third with the third, and the fourth with the fourth. So this just leads us to E energy squared over C squared minus the P vectors. And I have an issue that this is squared, so I have to write things up here, but it's also able to put the vector notion down there. So putting these two together, right, that was P squared here, and this was P squared here, we get that E squared over C squared minus P squared is the same as m squared c squared. So from this, we can add, multiplying with the c squared, we get that the energy is the same, or actually, no, wait a second. I could rewrite it saying that that the P mu leads to saying that this is energy squared minus P squared times C squared, where the P is a vector, it was a vector up here too, equals 2m squared, as it was here. I multiply with the C squared, so the C squared will become mc to the power of 4. Again, in a very, very special case, if our object is not moving, and its momentum is 0, so this leads to saying that E squared equals m squared c4, from which energy is the same as mc squared. Special case, special case. This is what really matters with the red. This is Einstein's energy momentum equivalence. The next big step in our journey is to introduce classical fields. So 2.3 will be classical field theory. So first of all, we should define what a field is. So in a field is essentially a mapping. It's a physical quantity which has a volume in each point in space-time. So to ct x, y, z, we map a volume. And this value could be a scalar, it could be a vector, it could be a tensor. This is something which actually I'm already discussing in one of the math background videos if you want to learn more about it. So in classical mechanics, we had a function of our coordinate, which depended on time, denoted as x t. And so from this, we will move to the field notion. So phi is going to be a function that, well, as I said, it's a mapping. So from the x and t coordinates, so from the space-time, we map it to y. And so we already introduced this new notion of x mu. So let's just use that. This phi is going to be now field, and it's going to be a scalar field. It assigns a number, and because of that, we call it a scalar field. So next thing that we should extend the definition of the Lagrangian. So the reminder is that the Lagrangian was, or the action actually, so not really the Lagrangian, but well, yeah, the Lagrangian and the action. So the action was defined to be the integral, the time integral of the Lagrangian function. But so now we want to move into a space-time integral, which I'm going to denote as dx to the power of 4. So we have the 3 spatial dimensions and the 4th time dimension. So we want to achieve the same thing, and so but that means we have to change the function in between. So we moved from the L to this curly L. And so the definition of the curly L will be that it's the other way around. Well, actually, yeah. So the definition of the L, the curly L, is that we get back the L if we do a 3-dimensional integral on the curly L. So the curly L is actually called the Lagrangian density. So Lagrangian density, while the L is the Lagrange function, or just the Lagrangian function. And actually, this leads to a new Euler-Lagrange equations, because we need to use the Lagrangian density if we want to speak about fields. So, but it's going to be very similar, that we are deriving the Lagrangian by the field. Earlier we derived the Lagrange function by the coordinate, which will equal to the derivative of the derivative of the Lagrangian. Remember, we were deriving by the derivative of q. So q dot was here earlier. So now we have the derivative of phi is noted with just this notion. So we derive by a derivative, and then there was another derivation by the time earlier. So that is now this part. So, okay, we could actually derive this with the second method. So earlier we were assuming that L depends on Q and Qt. And so we will do a very similar thing, saying that now the Lagrangian density depends on the field and the changes in the field, that is the d mu and the phi. And so earlier we were doing a discretization, we discretized the q and the q derivative, and so now we will do is the second method where we are doing the integration by parts. So again, we can do it this is we're doing this integral by 4 dimensions of this Lagrangian, which depends on phi, and the derivative of phi function. Okay, so then actually I did one more thing here, that I didn't put the dx to the end, but just next to the integral. It's somewhat simpler to remind that this is a 4-dimensional integral here. So the principle of least action says that when we are variating the action, so delta s should be 0. So let's just do that. Let's just variate this s. So from the s, we go to the delta s. We will still have our integral in these 4 dimensions, and we do derivation of L by the field multiplied with the change in the field, plus we do a derivation of L by the derivative of the field. So these were the two things the function depends on. So when I do a full derivation, that's what we get. So here to the delta, we put the derivative of the field. And I close the big bracket as well. So let's just look at the second term for a second. So in the second term, we have a derivation of a field and a variation of that field. So there is a mathematical theorem, Young theorem, which says that we can exchange these two things. So the derivative of the Lagrangian by the derivative of the mu, of the phi, sorry, multiplied with the variation of the derivative of the field is the same as, I will also just include the integral for dx to the power of 4. So that's the same as writing the integral sine derivative of the Lagrangian density by the derivative of the phi field and take out the mu and have delta phi here. So this is Young theorem that allows us to do this. And now we will do an inverse integration by parts. So this whole thing is the same as doing the integral of the 4 dimensions, the mu of the derivative of the Lagrangian by the derivative of the phi field and the phi, delta phi. If I do this, right, that means I need to derive this thing, plus I need to derive this thing. So when I do the derivation of this thing, that's not here, right? But when I do the derivative of this part, I keep this part, that's here. So in order to do that, I need to subtract something here. I need to subtract when I do the derivative for this part. So I need to subtract the integral of the x minus of 4 of the derivative by of the this part. So that derivative of Lagrangian density divided by the derivative of the field. And close this, and I have this d phi here. So I hope this is clear. So really what happened here is that we solved this. So that thing equals to saying that this is the derivative the Lagrangian by derivative of the field times the delta phi plus doing the other way around by keeping that R delta Lagrangian density of derived by the derivative of the field, and then I do the derivative on the second term, which was delta phi. Right, so, and then we want just this term, so we need to subtract this part. So when something like this happens, it is called a full divergence, that we are really doing the derivative of a function. And we can use the Gauss law for that. It is that we will have, when you have a divergence term in an integral, then actually, if you don't know this, then you should watch the math background video. This is the vector analysis part. So when we have a divergence of something, and then we can include it in the in the Gauss law and transform a function into a surface integral, and then we need to make the integral on this surface. But so essentially here these fields are really understood everywhere in space-time, and so the outcome of that is that we're taking an integral on this infinite surface, and that means that these fields will decay in infinity. So this whole thing is just going to be zero. Okay, I guess I should write down some parts of this. So using that red is a full divergence, can transform this to a surface integral where we take the boundary is infinity, and because of that the fields decay, so the fields go to zero, so the whole the mu part will be zero. So that means further equals, we continue in the green thing, if this is zero, then we are only left with this term. So that equals to the minus of the integral for this four-dimensional surface of the derivative of mu, the Lagrangian by the derivation by the derivative of the field. And we are left with the phi. This is what we have. So please remember that this whole thing was just the green part. So continuing the blue part is blue part was the delta of S, which you remember want to be zero, had the first part, which was this part, the derivative of the Lagrangian by the field multiplied with the variation of the field. So let's write it down. We have an integral, a four-dimensional integral of the derivative of the Lagrangian density by the field, multiplied with the change, the variation of that field. And now with the green, we learn that we also have this four-dimensional integral of the derivative of the derivative of the Lagrangian by the derivative of the field. and it's also multiplied with delta phi. That kind of makes us happy, because then we can just take off this delta phi and just write that this is a four-dimensional integral of these two terms, the derivative of the Lagrangian by the field and the change, or the derivative by the derivative of the Lagrangian by the derivative of the field. It's a really lot of derivations here, I know. And that was multiplied with this delta phi. So how can this all be zero for all delta phi? For all delta phi, it has to be 0. So that means that this term has to be 0, and then that will mean that the way that we can have this thing 0 is that if we equal the derivative of the Lagrangian by the field to be the same as the derivation of the derivative of the Lagrangian by the derivative of the field. And so this is the Euler-Lagrange equations for fields. So this is actually true for classical fields, for quantum fields. As of now, we are speaking about classical fields. So if you would want to describe, motion in a fluid, and this is what you would need to do. As the next step, let's define the conjugate momentum. Conjugate momentum. So this is going to be very similar to what we did in classical mechanics, where we had the generalized momentum. So if you remember, the generalized momentum was the derivative of the Lagrangian function. So the generalized momentum is going to be, first of all, denoted with a pi. So this pi is a field. So we have x mu here, and this is going to be the same as the derivative of the Lagrangian function, Lagrangian density, sorry, by the derivative of the field. So remember that earlier P was the derivative of the Lagrangian by Q dot. So that's kind of the direction we go here. We can also define the momentum density, which is going to be useful for the future. So momentum density is in uppercase pi, which is not really visible here. It has, though, a mu index. So it's a four-dimensional object, and it still depends on x mu, on the space-time. And earlier we had the time derivative here. Now we're going to have the full derivation by the mu of the field. So if you look at the time component, if mu is 0, so the pi, uppercase pi 0 in the x mu is actually the same as the lowercase pi x mu. And then the last thing for this video is Noether's theorem. Noether's theorem is one of the most interesting theorem. It can be also mathematical, but I think for now I'm not going to be super mathematical about it. I'm just going to say that if we have a continuous symmetry, Noether's theorem says that there is going to be a conservation law. So Noether was actually a mathematician, female mathematician, which is at that time was quite rare. And so it can be formalized in a mathematical way, but for physics, this really just means that if we have a continuous symmetry, um, if we have a symmetry, that means there is a conserved quantity, there is a conserved this conserved quantity is from the physics point of view is a conserved current that we will denote with J. If you did any electromagnetism, that you might remember that we had a lowercase j for the current. So here now we're going to do a four-dimensional current, which we denote with uppercase J. So J mu is the conserved current. So mathematically speaking, if a current is conserved, that means that it has no source or no sink. So if we do the divergence of that, so if we take the derivative of this J mu, then that leads to 0. So the examples are that if time is conserved, time symmetry means energy conservation. Then if we do displacement, and we get the same thing back, so that's a space symmetry. That means momentum is conserved. And rotational symmetries lead to the angular momentum being conserved. And so we can also do an integration of this. So if this is the current, the charge, which is not necessarily the electric charge, it could be any charge. The charge is defined to be the integral of this current. It's a three-dimensional integral of the zeroth element of this charge density J. Okay, with this we reached the end of the second video. We introduced several important concepts that we will use in the upcoming videos. As of now, we understand how special relativity works. We built up a principle that we can use to solve all classical mechanics problems. It's called the principle of least action. And we also introduced the idea of classical field theory. The next step in understanding the universe that is described by quantum field theories is to dive into the world of quantum mechanics. This is going to be the topic of the next video. As always, please like this video if you like it, ask questions in the comment section, subscribe to the channel so that you will get a notification when I upload the next video. Thank you.